Alright, here we are, day number 4 of Integrals 1 Calculus. We're going to cover the topics of U substitution, change the variable, and this thing called integration by parts. 3 different ways to integrate when it's not so clear what the integral might be. So let's get started. Again, here are some of the topics we're going to cover. U substitution is the reverse of the chain rule. Change the variable is very closely related. Integration by parts is the reverse of the product rule. Okay, and some trig antiderivatives as well as inverse trig integrals as well. So let's get started. Okay, so integration by U substitution. Basically what we want to do is we want to identify whether or not these two functions here are related. Alright, so if one of them could possibly be the derivative of the other, then we're in. Then we go with this idea of U substitution. So if you'd like to, you can look this over. I'm not going to cover it too much in depth, but what you will see here is that here, x squared plus 3x, if I took the derivative of x squared plus 3x, what do I get? I get 2x plus 3, and go figure that shows up here. So these two are very closely related in that way. Therefore, we can use this idea of U substitution, of which I'm going to model that right now. So proof here if you want to check it out. Otherwise, I'm going to just jump into some examples. Alright, so let's look at part A first. So the first thing I want to do is try to identify some function or some expression for U. Typically, if you have a rational function and you end up using U substitution, U ends up in the denominator. Typically, but not all the time. So let's say that's what U equals. Alright, so then du with respect to x would be 3x squared plus 2. Look at that. Okay, so I'm going to do one quick modification. And from now on, I'm not going to write du dx. I'm going to write du equals, and then put the dx on the end of the derivative. Okay, so that's a perfect match. So now I can replace all of that with du. So I'm going to go ahead and do that. This will now be the integral of 1 over, we've called this here u, and du fills in the rest, right? So I've filled all this in, substituted in 1 for that. And then this in the denominator is u. So now I can take the integral of 1 over u with respect to u, which is the natural log of the absolute value of u plus c. I have to do one more thing and sub back in what u equals, which is x cubed plus 2x, and I'm done. There's your integral. You could always test that by taking the derivative. Let's move over to this example. Okay, another good method here is to identify, right, I've got two functions x and I've got e to the 1 minus x squared. So I'm going to look in the exponent here, and I'm going to call the u 1 minus x squared. So du equals negative 2x dx. That's really close to x dx, really close. So what I'm going to do is I'm going to bring that negative 2 over, and now I have what I want. So I'm going to sub in this for x dx. So now my integral will be, I'm going to bring that negative 1/2 out in front, and I'm going to leave the du in the back, and I'm going to take e to the u, right? E to the u, right? And u was 1 minus x squared. So now I can integrate, and clearly the integral of e to the u is e to the u. E to the u is e to the 1 minus 2x, 1 minus x squared, and that'll be multiplied by 1/2. Don't forget to add C. Let's try another one. Okay, this one's a little funky, but I would nest my u value in the more complicated of the two functions. In this case, sine and cosine work out well, so I'm going to call u cosine of x. Not cosine cubed, just cosine of x. So du will equal negative sine of x dx. I don't want negative sine, I want positive sine, therefore negative du equals sine x dx. I'm trying to manipulate this to get what I have. Alright, sounds like my 3-year-old. Integral of cosine of x cubed, well that's u cubed, and sine of x dx gets substituted in by using negative du. What a simple integral now. So this would be u to the 4th over 4 plus c. Don't forget your negative. What is u? U was cosine. So I have negative cosine to the 4th x over 4 plus c. There you have it. Let's try another one. You can stop the video if you'd like to. Like I said, when you have a rational, typically u ends up in the denominator. Ooh, this one's going to be nice. So du equals cosine x dx. Perfect match, right? If I wanted that dx here and it's taking the integral of that. So perfect match. So that would make this integral the integral of, look, I've got cosine x dx. I'm going to replace that with du. Put 1 over sine x, which is u. So the natural log, the integral of 1 over u is the natural log of u plus c. And u, of course, is sine x. Here's your integral. Alright, so I want to work part A over here for a second. You might be thinking, oh yes, u is x squared minus 1. Good, that's good. That's a good thought. I like it. Okay, I see an x dx, but I don't see a 2x dx, so I'm going to bring that 1/2 over. There's a nice substitution. So this integral would be the integral 1/2 the integral of the x dx is taken care of by the 1/2 du. This would be u, which is x squared minus 1 to the 1/2. So it looks like I would get 1/2 u to the 3/2 times 2/3 and plus c. So the 2's would cancel. I'd get 1/3 u to the 3/2. So that would be x squared minus 1 to the 3/2 plus c. Cool. So why am I doing this again? Because there are scenarios where u substitution doesn't work, like part B. Right? If I try u equal to, let's say, x minus 1, what is du? Well, then du is just dx. So I've taken care of this, but what do I do with that? Okay, so what you do is you take this expression and you manipulate and solve for x. X would equal u plus 1. So now I know x equals u plus 1. This integral, direct substitution for x, is u plus 1 times, I have u to the 1/2 du. Okay, so what do you do from there? Well, I would distribute this to both u and to 1. So what would that become? That would become u to the 3/2 plus u to the 1/2 du. And now I can integrate relatively easily. This is called, what is it called? It's called change the variable. Right? So if you can't use u substitution, change the variable might be an option. So this would be u to the 5/2 times 2/5 plus u to the 3/2 times 2/3 plus c. We got a little bit more to do. What was u? U is x minus 1. So that's 2/5 x minus 1 to the 5/2 plus 2/3 x minus 1 to the 3/2 plus c. That's called change the variable, folks. Alright, so let's try it here. Alright, I even gave you the first couple things here. So if u is x plus 2, and du dx, alright, which just means that du equals dx, right, is said thing, then this integral, what I'd want to do is I'd want to solve for x here first, which would be u minus 2. So this would be the integral of u minus 2, right, direct substitution for x, times u to the 1/2. So very similar to what we just did. Alright, go ahead and do this on your own and check your answer in a moment. Alright, there you go. That's the answer I'm getting. Hopefully you get the same thing. Let's move on. Okay, if this doesn't sit real well with you to start, then that's okay. Alright, this is called trig substitution, and I didn't want to cover this in depth today, but I'm gonna, because this was on the notes, I'm gonna go ahead and do it. Okay, I'm giving you that I want x to equal 3 secant theta, and that d theta, right, equals 3 secant theta tangent theta. I'm going to write a couple things out and I'll explain. Okay, if you would follow with me. X equals 3 secant theta, so I did a direct substitution here and here. We found that dx, I just multiplied both sides by d theta, is 3 secant theta tangent theta d theta. So I put that on the end, substituting n for dx. So as I simplify, I can do some simplifying immediately. I would get 9 secant squared theta minus 9. And what will happen here is I'll get a cancellation of 3 secant theta with 3 secant theta. So I'll get this times tangent theta d theta. Okay, I'm not real happy about how weird this looks right now, so I'm just going to adjust. Okay, there we go. Alright, so a couple things I can do here. One is I can factor out a 9, which makes this secant squared theta minus 1. Okay. And then I could bring that 9 out, right? The square root of 9 is 3. And what I'm going to do is I'm going to change this. So the 9 popped out of the square root and became a 3. I'm going to change that to tangent squared theta, right? That's an identity. Secant squared theta minus 1 equals tangent squared theta. So have that in your back pocket. Alright, and that times tangent theta d theta. Now, let's do a little bit more manipulation here. This square root and this square, or the square and the square root will cancel each other. So therefore I'll have 3 times tangent theta d theta. So that'd be tan squared theta d theta. Okay, so I'm going to pull that 3 out of there for just a second. And the integral of tangent squared theta d theta, I'm going to rewrite as secant squared theta minus 1. No, what the heck? You're going back and forth. Well, I had to break that out of that square root up here, right? This square root right here, I had to break it out of there by turning it into one term. And then I'm going to go back to it because it's going to be easier to integrate. Therefore, I'm going to take the integral of secant squared. Well, the integral of secant squared is tan theta. And the integral of negative 1 is negative theta. Okay, and when I distribute, I get 3 tan theta minus 3 theta plus c. That is trig substitution method of integration. We're going to cover that in much more depth later on. Okay, integration techniques continued. This is called integration by parts. Integration by parts. This is the opposite operation of the product rule, and I'm about to show you how the product rule shows us this formula. Okay, so I'm going to take the derivative of u times v. All right, and that's just product rule. That's all that is. So if I do that, I get v times the derivative of u plus u times the derivative of v. Okay, now I'm going to integrate both sides. Integrate both sides, integrating all three of these terms. Okay, so what do I get? Well, the integral of a derivative on the left side will just be u times v. On the right side, I get integral of what we're going to call, just for a moment here, v du, right? Just derivative of u, plus the integral of u dv. Okay, so what I want is I want to isolate this, and there's a reason for that. So I'm going to isolate it all by itself. The integral of u dv is equal to, and that'll be equal to uv minus the integral of v du. What does that tell us? That tells us if two functions, if we know that one of them, this one is just a function, and this one is a derivative of some function, then we can use those in order to figure out what the actual integral is. It'll be much more clear here in a moment how this works and why it works. Okay, so it's the opposite of the product rule. Now I've got a pretty loaded slide here, so I'm going to try to explain. We always, looking over here at this LIATE acronym, we always put U's up, we always put DV's down. Okay, so U's are up and DV's are down. So what does L mean? L means any sort of logs. That is highest priority. Next priority is inverses. Next priority after that is anything algebraic. What I call algebraic, like a polynomial of any sort, x squared, 3x cubed, whatever. T is for trig, I'm sure you could have guessed that, and E is for exponentials. So let's look at the example we've got here, and let's remember that the integral of u dv equals u times v minus the integral of v du. Okay, so let's come up with what we've got here. Okay, x. Where does x fit on our LIATE table? Well, it would be algebraic. Where does cosine fit? Well, it fits trig. Therefore, I'm going to call x my u. Okay, x is going to be u, and cosine is going to be my dv. Okay, so x is going to be my u. So du, right, if I take the derivative of x, I get 1 dx. Okay, so du is going to be dx. Okay, that's what this is. All right, dv we said was cosine of x dx. So what is the integral? All right, if I want to go from dv back to v, that would have to be sine of x. So what I'm told here is this. U is x, du is dx, dv is cosine x dx, v is sine x. Now we can fill this out and do some integration. So the integral of x cosine of x dx is equal to uv. That would be x sine of x. This is u, this is v. Okay, minus the integral of v du. Okay, so v is sine x, du is dx. Now we can integrate and finish this one up. So nothing changes with uv, but the integral of that would be negative cosine of x, and that would be x sine x plus cosine x. That would be our integral of x cosine of x dx. Don't forget plus c on the end. That is your first attempt at integration by parts. Let's try another. Okay, LIATE, U's up, dv's down. Okay, we've got an algebraic function x. we've got a exponential function e to the x. So it looks like x will be u and e to the x will be dv. X is u, so that makes dx equal to du. dv is e to the x dx, and so therefore the integral of e to the x is itself. So this will equal integral of x times e to the x dx will be u times v, which is x e to the x, minus the integral of v du. E to the x, du is dx. So the answer is x e to the x minus integral of e to the x is itself plus c. Integration by parts, you aren't so bad. Okay, this one can throw some for a loop. I'm going to write 1 times the inverse cosine of x. Okay, so u's up, dv's down. U's up, dv's down. U is going to be the algebraic. Okay, I was mistaken there. I had written 1. Okay, well, 1 is algebraic, right? And inverse cosine, oh, there it is, never mind, is higher on that priority list, right? So, looks like inverse cosine is going to be u. The derivative of inverse cosine is -1 over the square root of 1 minus x squared dx. So dv will be 1. That means we would have x, 1 dx. Therefore, we would have x as v. So here we go. uv, which is x, and I'm going to write this, I guess I'll stick in inverse notation, minus the integral of v, oops, let's write it this way. Let's pull that negative that was in here out here, make that a plus. That would be x times, or x over 1 minus square root of 1 minus x squared dx. Okay, so what? How do I do that, huh? Okay, well, here's how you do that. That's a u substitution problem, just waiting. Right, let's do this by u substitution. What should u equal? How about 1 minus x squared? So du would equal -2x dx. I don't have a 2x dx, therefore I'm going to factor, or I'm going to bring that -2 over as -1/2 du. Therefore I have x dx. So that ultimately what that would be is the integral. Okay, x dx is going to be replaced by -1/2 du, and 1 minus x squared would be 1 over the square root of u. So we need to integrate that. No change here. I'm going to bring that -1/2 out, and I'm actually going to write this as u to the -1/2 du to make it easier to integrate. Okay, so here we go. We got x times inverse cosine of x minus 1/2 times the integral of that would be u to the 1/2 times 2. And we'll throw that plus c on the end. Okay, so x times cosine inverse of x minus, looks like 1/2 would distribute and just turn that into a 1. And u now has a different value, right? Don't get fooled into thinking it's the u over here, because it's not. It's the new u, and if you wanted to use a different variable, you could. So it would be square root of 1 minus x squared plus c. Okay, that's an interesting one that's got integration by parts, and it's got u substitution involved. Okay, important challenger. We're going to save this one for class. This is a really good one. But that is the end of lesson 4 on all sorts of stuff. U substitution, integration by parts. Trig substitution, change the variable. Hope you have a great day. Look at all these beautiful leaves. Oh, that's beautiful. Okay, have a great day.